January 30th, 2024. The Red Sea, USS Gravely. A Houthi anti-ship missile screams toward the destroyer at Mach 2, 5 seconds from impact. Too close for standard missiles, too close for ESSM, too close for anything except the last weapon that fires before physics makes interception impossible. A burst of white smoke. A missile smaller than a person launches from the deck, 9 feet long, 160 pounds, and in those final 5 seconds, it does what billion-dollar radar systems and multi-million-dollar interceptors couldn't. It stops the threat 1 mile from impact, close enough that debris splashes near the ship, far enough that 300 sailors go home alive. This is the RIM-116 rolling airframe missile, the smallest naval interceptor the United States has ever built, and the reason destroyers survive when everything else fails. Because when threats penetrate outer defense layers, when reaction time collapses to seconds, when human decision-making is too slow, you don't need the biggest weapon. You need the fastest, the most automated, the one that fires without asking permission. And at 9 feet long, RAM is small enough to pack dozens on a single ship, cheap enough to fire in salvos, and deadly enough that adversaries who thought they penetrated American defenses die 1 mile from victory. Let me show you why smaller is deadlier, why automation beats human reaction, and why the last line of defense is the most important one. The problem is terminal phase, that final stretch when anti-ship missiles are seconds from impact, maneuvering violently and traveling too fast for traditional defenses. Standard missiles engage at 50 to 100 miles. Evolved Sea Sparrow at 30 miles. Both excellent systems, both useless if the threat gets through, and threats get through. Radar horizons limit detection range. Sea-skimming missiles hide behind wave clutter. Coordinated attacks overwhelm defenses. Electronic warfare blinds sensors. One way or another, something always leaks through the outer layers. That's when RAM fires. The missile weighs 162 pounds, fully loaded, 9 feet long, 5 inches in diameter. You could fit 6 rams in the space occupied by one standard missile. And that ratio matters, because when threats arrive simultaneously from multiple vectors, magazine depth determines survival. The ship with more interceptors lives. The ship that runs out dies. USS Arleigh, Burke-class destroyers carry 2 ram launchers with 21 missiles each, 42 interceptors dedicated purely to last-ditch defense. That's 42 chances to stop leakers before they kill the ship. Older ships relied on Phalanx CIWS, the iconic Gatling gun. 20mm tungsten rounds fired at 4,500 per minute, creating a wall of metal. It works, but it has limitations. Effective range is less than 1 mile. Against supersonic missiles, that's 2 seconds of firing time. Miss, and the threat impacts. Phalanx also struggles against multiple simultaneous threats. It engages one target at a time while others close uncontested. RAM solves this. 15-mile engagement range. Multiple missiles can engage multiple threats simultaneously. And unlike guns that need proximity, RAM kills at distance, destroying threats before they enter gun range. The guidance system is elegant in its simplicity, dual-mode passive homing. The missile doesn't need the ship's radar. It doesn't need external guidance. It homes autonomously on the threat itself. The first mode is radio frequency homing. Anti-ship missiles emit radar signals while searching for targets. RAM detects those emissions and flies directly toward the source. The attacker's own radar becomes a homing beacon. The second mode is infrared homing. As the missile closes, an imaging infrared seeker activates, tracking the thermal signature of the threat's exhaust and airframe heating. Even if the threat shuts off its radar, RAM maintains lock-through thermal tracking. Dual mode means the missile never loses track. Radar or infrared, one sensor always has the target. And because both modes are passive, RAM doesn't emit anything the enemy can detect. It's invisible until impact. The warhead is small but sufficient. 25 pounds of high explosive with proximity fusing. When RAM passes within lethal range, the warhead detonates, creating a fragmentation pattern that shreds incoming missiles. A 25-pound warhead sounds inadequate until you understand the target. Anti-ship missiles have thin airframes optimized for speed and range, not durability. They carry fuel, guidance systems, and warheads in lightweight structures. RAM doesn't need to vaporize them, just damage them enough that they lose guidance, tumble, and miss. A destroyed control surface means the threat can't maneuver. A ruptured fuel tank means it loses power. Fragmentation through the guidance section means it goes stupid and flies ballistic. Any of those outcomes means the ship survives. But the truly revolutionary aspect is automation. RAM operates in autonomous mode. The system detects threats, prioritizes targets, and fires without human intervention. That sounds dangerous until you understand the timeline. A supersonic anti-ship missile at 1 mile is 2 seconds from impact. Human reaction time is 0.2 to 0.3 seconds. Processing the threat, deciding to engage, and issuing fire commands takes another second or more. By the time a human responds, the threat has already hit. RAM's computer makes those decisions in milliseconds. Threat detected, trajectory calculated, launch decision made, missile away, all before a human brain finishes processing what's happening. That automation is the difference between interception and catastrophe, and it's why RAM exists. The system was developed in the 1970s as a joint US-German program. The United States provided the Sidewinder guidance system. Germany provided the airframe. Both nations needed a point defense weapon that could stop Soviet anti-ship missiles in their terminal phase. Production began in 1992. Initial deployment was cautious, limited to high-value ships like aircraft carriers and amphibious assault ships. The concept was proven, but the Navy wasn't ready to commit. Then they tested it in realistic scenarios, multiple supersonic targets simultaneously, sea-skimming profiles, electronic warfare, everything that makes terminal defense impossible. RAM worked, not perfectly, but reliably enough that the Navy started installing launchers on every major surface combatant. Today, over 150 U.S. ships carry RAM. Carriers, destroyers, cruisers, amphibious ships, even literal combat ships. Every platform that goes in harm's way gets RAM launchers, and international sales reflect confidence in the system. Germany, South Korea, Japan, Greece, Turkey, Egypt, and others operate RAM. Over 1,000 launchers deployed globally. Thousands of missiles produced. That's not experimental technology, that's mature, combat-proven defense. The launcher itself is distinctive. A 21-cell cylindrical unit that looks like a miniature naval turret. It rotates to face threats, elevates to optimal firing angles, and launches missiles in rapid succession. Reload time is the limitation. Once 21 missiles are expended, the launcher is empty. Reloading requires port facilities and cranes, but 21 interceptors per launcher times 2 launchers equals 42 last-ditch defenses. No ship has ever fired all 42 rams in combat. Even in the Red Sea operations where destroyers fired 80 standard missiles, ram usage remained limited, because by the time ram fires, something has already gone very wrong, and that's the psychology of last-line defense. Crews pray they never need it, but when they do, when threats are seconds from impact and outer layers failed, RAM is the only option remaining. The cost is reasonable compared to alternatives. Each RIM 116 Block 2 missile costs approximately $900,000. That's expensive for a small missile. It's cheap for preventing ship loss. A standard missile costs $2 to $4 million but engages at long range. ESSM costs $1.5 million and handles medium-range threats. RAM at $900,000 handles terminal threats nothing else can stop. The cost gradient makes sense. More expensive interceptors for earlier intercepts, cheaper interceptors for last-ditch defense when the alternative is losing a multi-billion-dollar ship. And magazines matter. At $900,000 per missile, equipping a destroyer with 42 rams costs $38 million. That's 2% of the ship's construction cost. Marginal investment for maximum survival capability. The Block 2 upgrade added infrared imaging and kinematic improvements. Earlier variants used simpler infrared seekers that tracked heat sources. Block 2 uses imaging infrared that sees target shapes, defeating flares, and identifying specific threat types. Kinematic improvements mean faster acceleration and tighter turns. The missile pulls higher Gs, maintains energy better, and intercepts maneuvering threats more reliably. Block 2A, currently in production, adds millimeter wave radar for improved all-weather capability. Infrared struggles in rain, fog, and sea spray. MW radar penetrates those conditions, ensuring RAM works regardless of weather. Each upgrade increases reliability without changing the fundamental design. The missile remains 9 feet long, 160 pounds, and compatible with existing launchers. Ships get improved capability through software updates and missile replacements, not expensive launcher modifications. That upgrade path ensures RAM remains relevant for decades. As threats evolve, RAM evolves. As adversaries develop countermeasures, RAM adapts. The core concept, small, fast, autonomous, terminal defense, remains valid. The operational record speaks clearly. RAM has been tested over 200 times since entering service. Success rate exceeds 95% in realistic scenarios. That includes simultaneous engagements, electronic warfare environments, and supersonic maneuvering targets. Combat use remains classified, but analysts confirm RAM intercepted threats during Red Sea operations. Exact numbers aren't released, but the fact that no American ship was struck despite hundreds of missile attacks suggests terminal defenses worked as designed. The strategic implications are profound. Adversaries design anti-ship missiles to overwhelm defenses through speed, maneuverability, and numbers. They assume penetration of outer layers means mission success. RAM denies that assumption. Even leakers face a final layer of autonomous defense that engages in seconds and kills reliably. The attacker's calculation changes. Instead of needing to penetrate standard and ESSM, they need to penetrate standard ESSM and RAM, and surviving RAM requires getting past 21 autonomous interceptors per launcher while traveling at Mach 2 under G forces with less than 2 seconds to impact. That's not difficult. That's nearly impossible. China develops carriers. Russia builds cruisers. Both face the same problem. Their multi-million-dollar anti-ship missiles must survive American terminal defenses that cost a fraction as much and work autonomously. The economics favor defense. Spending $900,000 to stop a $2 million missile is profitable. Spending $40 million in RAM to protect a $2 billion destroyer is essential, and the layered defense concept multiplies effectiveness. Standard kills at long range. ESSM kills at medium range. RAM kills in terminal phase. Phalanx provides gun backup if everything fails. 4 layers, each designed for specific ranges, each automated, each proven in testing and combat. Adversaries must penetrate all 4 layers simultaneously while under electronic attack, facing decoys, and operating in degraded sensor environments. The probability of successful strike collapses, not impossible, but improbable enough that massed attacks become necessary. And massed attacks mean expending dozens of expensive missiles to kill one ship. That exchange rate doesn't favor attackers. The future is CRAM, an upgraded launcher integrating RAM missiles with Phalanx radar systems, better threat detection, faster reaction, enhanced tracking. The missile remains identical. The launcher gets smarter. Ships equipped with CRAM gain capability without losing magazine capacity, and production continues. Over 100 missiles manufactured annually, sufficient to replenish expended stocks and equip new ships as they commission. The supply chain exists. The industrial base is proven. The technology is mature. Everything needed for sustained production during prolonged conflicts already exists. Compare that to experimental systems requiring years of development and uncertain production timelines. RAM is here now, working, and available in sufficient quantities to equip the fleet. International cooperation strengthens the program. Germany, the original partner, continues development and production. Allied navies share operational data, improving tactics and employment concepts. When South Korean destroyers face North Korean anti-ship missiles, they use RAM. When Japanese ships defend against Chinese threats, they use RAM. When NATO operates in contested waters, RAM provides terminal defense. The standardization means training transfers between navies. Tactics developed by American crews apply directly to Allied ships. And in coalition operations, every ship knows what every other ship's terminal defenses can do. That interoperability multiplies effectiveness. A carrier strike group with 10 escorts doesn't have 10 independent defense systems. It has one distributed network where every ram launcher protects every ship through coordinated engagement zones. The smallest naval missile ever built isn't trying to be the best at everything. It's optimized for one mission: stopping threats in the final seconds before impact when everything else failed. 9 feet long, 160 pounds, passive guidance, autonomous operation, and a track. Record proving it works when ships need it most. Adversaries who think penetrating outer layers means success learn otherwise, because RAM waits at 1 mile, invisible, autonomous, and absolutely lethal to threats that thought they'd already won. Size isn't weakness, it's specialization. And 42 specialized interceptors defending a single ship mean that even perfect attacks face imperfect odds. The largest missiles engage at hundreds of miles. The smallest engage at 1. But when that 1 mile is all that remains between a threat and a ship, small becomes the most important weapon aboard. USS Gravely survived January 30th, 2024 because RAM worked, 5 seconds from impact, close enough to see debris, far enough to survive. That's not luck, that's engineering. And it's why the smallest naval missile ever built is the one adversaries fear most, because big missiles are impressive, but the small one that fires last is the one that decides whether you go home, and RAM always fires last.